Question 2. A steel sphere of mass 0.29 kgs is suspended in equilibrium. Now, those are the keywords you must note when you're reading a question. Suspended in equilibrium, meaning that the resultant force in any direction is 0, and the resultant moment in any about any axis is also 0. So it's suspended in equilibrium from a vertical spring. The center of the sphere is 8.5 centimeters from the top of the spring as shown in Fig 2.1. So check Fig 2.1 there. Okay. So if it is in equilibrium, then the question is, who were we told that it was in equilibrium? The steel sphere. So we don't just read questions and move on. The steel sphere is in equilibrium. They didn't talk about anything else other than the steel sphere. So if it is suspended in equilibrium from vertical spring and it is in equilibrium, we know that anything with mass, as we are told that it has a mass, has a weight. So if it is in equilibrium, where does weight go? We know that weight always acts vertically downwards, like that. So if it has a weight going vertically downwards, for it to be in equilibrium, then someone must be balancing that weight such that there must be a force in the opposite direction balancing this weight so that the resultant force in the vertical direction is 0. That way it can be in equilibrium. So it is common sense that since there's a spring here, it is probably stretched. And from Hooke's law, it is known that when you apply a load to a spring, there's going to be an extension. So if there's going to be an extension because you've applied a load in the spring, then there's a tension in the spring, there is an extension. So in other words, when there's an extension, then there's a tension or an applied force in the load, in the spring. So we can agree that there is a force in the spring acting on the sphere. Just like the sphere is applying a force on the spring. If we are to apply Newton's third law, the spring is applying a force on the sphere, and the sphere is applying a force on the spring. Of course, these forces don't cancel out because they're acting on different bodies. So the spring is applying a force, a vertical force, on the sphere. But the sphere, which is pushing downwards, pulling downwards because of the weight, it's applying a downward force on the spring. I hope that we understand that. And that downward force is what we call this load, which causes the extension. That downward force is being applied by the sphere on the spring. But the spring is applying an upward force on the sphere to obey Newton's third law. And we are only interested in the upward force applied by the spring on the sphere, because that upward force is the one that is counteracting the weight of the sphere, such that if they are equal, because there are no other sources of forces here visible, and this is said to be suspended in equilibrium, so these forces are equal. So we now know the force acting on the sphere by the spring, which then happens by Newton's third law to be the force acting on the spring by the sphere. I hope I'm clear there. Okay, so we continue. So we now know that the force originally in the sphere, in this case, has to be, the force, in the spring has to be 0.29 times 9.81, because that is the force that is balancing out the weight. The sphere is now set into motion so that it is moving in a horizontal circle at constant speed. So the moment they talk about something moving in a horizontal circle at constant speed, we know that this is circular motion, and there must be a centripetal force and a centripetal acceleration. Automatically, this is a must. It's a must. Okay, fine. The distance from the center of the sphere, that is here, to the top of the spring, that is here, is now 10.8 centimeters. Originally it was 8.5. Now it is now 10.8 centimeters. We can even deduce there that the extension has increased, meaning that the force in the spring has increased. Okay, fine. The distance from, okay, explain with reference to the forces acting on the sphere why the length of the spring in Fig 2.2 is greater than in Fig 2.1. Now, remembering Hooke's law, remember as I told you, for there to be an increase in extension, there must be an increase in load in the spring. So our only question, as the question was already hinted to us, is to justify that there are more forces. So we have to account for where those forces are coming from. Seeing as we still have the same mass, the same sphere, whose weight is going downwards. So the question is, if we still have the same sphere, whose weight obviously will be going downwards, where are we now getting the additional forces such that in the spring now there is now more force, seeing as there is now more extension? If this one was just 0.29 times 9.81 and this one was only capable on its own to increase the length of the spring to 8.5 centimeters. So we have to account for the emergence of the other forces. So to be technical about it, we know definitely that if this is to move in a circle, I'm not going to go into the intricacies of centripetal force, but centripetal force is a resultant force which has to be supplied by someone. So someone is supplying a centripetal force. How do we know? We have an object moving in circular motion. For it to be moving in circular motion, it must have an acceleration called the centripetal acceleration. And for that to happen, there must be a centripetal force, which is more like a resultant force. And the resultant force is not a force on its own. It's a result of forces being applied. So the question is, who is applying that force? Now, we do know that there is tension in the spring. So if there is tension in the spring, as you can see, and also the spring is making an angle which is less than 90 to the horizontal, then it means that the tension in the spring, there has to be a tension in the spring there. The spring is forced to have a tension in a way, just like it was forced to have a tension just like there's a tension. It was supposed to be a tension when there was a weight of the sphere going downwards. Now here again, a tension is forced because there is a demand of a centripetal force, because this is moving in with circular motion. So the demand for a centripetal force, is met by the component of the tension in the spring that is horizontal, like that. So the component of the component of the tension horizontally has to supply the centripetal force. Otherwise, this will not move in a circle. This is the only force, the tension in the spring, that is having a component that can go horizontal among the forces given here. The next, we also know that this still is in equilibrium. This still sphere is neither going upwards or downwards, meaning that vertically it has a resultant force of 0. Meaning that since we know that there is only one vertically downward force, which is the weight, so the force or whatever component of force going upwards has to be equal to that weight. And what is that component of force going upwards? Is the component of this tension. So in other words, just this fraction or a component of that weight is equal, a fraction of that weight is equal to match the weight, which means that the tension is no longer, because we're talking about the component of the tension is equal to vertically upwards is equal to match the weight, meaning that the tension now is now bigger than the weight. So if the tension is now bigger than the weight, so what does it mean? It means that the tension is doing two things. Number one, it is supplying, either the component is supplying the horizontal needed force, the horizontal centripetal force that is required for keeping this in equilibrium, keeping this moving in circular motion, and the vertical component of the tension is supplying the force needed to balance out the weight. So it is obvious that the tension is bigger. Or we could say that the horizontal and vertical component combine to form a bigger force which is a tension, because so that tension is bigger than the weight. So now that we have a force bigger than the weight, and originally we had a force equal to the weight, it means that we have increased the load in the spring, causing the extension of the spring. So I'll just read my answer here as I've written. The horizontal force on the sphere causes the centripetal acceleration. True, as I've said. Hence, centripetal force. So the horizontal force, which is the horizontal component of tension on the sphere, causes the centripetal force and acceleration. Weight of the sphere is now equal. Weight of the sphere is now equal to the vertical component of tension, as I've already explained. How do we know? Because the sphere is neither moving upwards or downwards. Then the horizontal and vertical components of force now combine. So those horizontal and vertical components of force, which are demands, by the way, if this sphere is to remain in vertical equilibrium, neither moving upwards or downwards, then there must be a vertical component of tension, which is supplying a force equal to the weight. If it is to be moving in a circle, then there must be horizontal acceleration and horizontal force supplied by the component of tension again. So this horizontal component of tension and the vertical component of tension combine to give us a greater tension. Why do we say a greater tension? Because this tension is bigger than the original tension which was there, which was equal to the weight. So the greater tension in the spring results in the greater extension of the spring. That's why we now have 10.8 as our new length of the spring. Okay, next part of the question asks, the angle between the linear axis of the spring and the vertical is 27 degrees. Show that the radius of the circle is 4.9 centimeters. So we need to understand what we're talking about here. Let me erase everything here. So the question is demanding from us to show that the radius of the sphere is what? It's 4.9. So let me draw this. Then I'll draw this triangle. Then let me complete the triangle. Okay. Now, this is the radius of the sphere, of the circular motion. But there is an angle of 27 here for a line crossing. Okay, let me draw a more straight line. For a line crossing here and here, there's an angle of 27 here. So likewise, there will be an angle of 27 there also. So if there's an angle of 27 there, and the length from this point is indicated by here to here, if that length is 10.8, then we can find R using SOHCAHTOA. Obviously, we have hypotenuse. We need to know the opposite to the 27 degree angle. So what do we do there? It is obvious that we have to use sine 27 equals to opposite, which is the radius, over hypotenuse, which is 10.8. Then we multiply both sides by 10.8, which is what I did here. So I said the radius is 10.8 multiplied by sine 27. So you must know where it comes from. We don't need to memorize, which gives us 4.9. Then the next part of the question says, show that the tension in the spring is 3.2. So we have to show that the tension is 3.2. Now we go further again. We need to show that the tension in the spring is 3.2, sorry. So to show that the tension in the spring is 3.2, we need to have something that we can equate to that tension. For example, we don't know the centripetal force as of now. So we cannot equate the component of the tension horizontally to the centripetal force. But we do know the weight. And we know that the component of the tension vertically is equal to the weight. So the component of the weight vertically, that would be that. If that is the component of the tension vertically. Now, considering that this angle here and this other angle here make a Z angle, so there is 27 degrees also here. So if we say that the tension is T, its component of the tension vertically would be T cos 27, and the weight is 0.27. 29 times 9.81. So we equate this and we are able to work for tension. So this is what I did here. I said T, the tension, cos the angle theta is equals to mg, the weight. Then we substituted the angle theta, which we know to be 27, and the mass and the gravitational field strength, and we found our tension to be 3.2, like that. Now, we are told then that the spring obeys Hooke's law. If it obeys Hooke's law, it means that obviously, by obeying Hooke's law, it means that the applied force on it is equal to kx, or applied force is directly proportional to the extension at all times during its loading. So calculate the spring constant in Newton per centimeter of the spring. Now, to find the spring constant, we have to understand that we have been told that it obeys Hooke's law. Now, F is in a way proportional to x. Now, what is the general implication that F is proportional to x? The implication that F is proportional to x means that if we double F, what we do to F also happens to x. So if we double F, we have also doubled x. That's what it means. I'll repeat again. If we double F, then we have also doubled x. Now, to give for context, let's say that if F was 2 and x at that particular time was 1, if F is doubled, then it becomes 4, and x will also be doubled to become 2. And if F is tripled, it becomes 6, and x is also tripled to become 3. Now, there's another consequence to this. The consequence to this is that if I were to subtract this 6 and this 2, and I subtract this 3 and this 1, I would be able to find the spring constant. Now, what do I mean by that? What I mean by this one is this, is that if I were to draw a graph of force against extension, that graph will be a graph passing through the origin. Sorry, this does not pass through the origin. Let me leave it like that. So if I were to take a value where I take a value of x and a value of, a value of x and a value of f, and another value of x and a value of f, if I find the change in f, which will be delta f, and if I find the change in x, which will be delta x, then I would have found the gradient of the graph. By finding the gradient of the graph, since f is equal to kx, then the gradient of the graph will give us the spring constant, right? So here's the trick now. If for this force now, if we did not know, for instance, for this force, the original force was just the weight, 0.29 times 9.81, and there was the new force now, which is 3.2. Now, we did not know exactly the actual extension, but we knew the new length. So we could say that the new length, 10.8, plus the actual length, the original length, then minus the, if I say the new length minus the original length, this gives me the extension at a particular time when we have got the force of 3.2. Okay? And if I say minus, let's say 8.5 minus L, the original length. 8.5 minus L gives me also the extension at a particular time when the load was equal to 0.29 times 9.81. Me subtracting them, what am I doing exactly? I'm subtracting the two extensions, because the extension at this particular instance, which is 10.8 minus L, and the extension at this particular instance, which is 8.5 minus L. Subtracting these two extensions gives me the delta x which I want, right? And subtracting 3.2 and 0.29 times 9.81 gives me the delta f which I want. So if I have delta f over delta x, I find my spring constant. So if you can see here, this becomes 10.8 minus L minus 8.5, but then this becomes plus L. So minus L and plus L becomes 0. So 10.8 minus 8.5, that's what we get here. So subtracting 10.8 minus 8.5 is the same thing which will give us our delta x. So I want you to not be mistaken when we actually do it. So the first one now, I'm finding my delta F. Of course, I call it delta T because it's a tension in the spring, but it's just the delta F anyway. It's 3.2, the new force, minus the old force, 0.9 times 9.81. Then I have already said here, spring constant is equal to the gradient of that graph, delta T over delta X. In which case, delta x, we showed that it can be found by saying 10.8 minus 8.5. So if that is clear, then it is apparent that we don't need to worry at all. 10.8 minus 8.5 gives us the extension delta x, as I've justified. Ultimately, when you punch this in, you get 0.15 per centimeter, which is our spring constant. Use the information in B. With B, the previous question that we just did, all of it, B1, B2, B3, to determine the centripetal acceleration of the sphere. Now remember, I've been telling you that the horizontal component of the tension gives us the centripetal acceleration. Now we now know the tension by the way. We now know the tension, that is 3.2, and we know that the horizontal component of it will give us the centripetal force. And if we find the centripetal force, we'll find the centripetal acceleration, since we know the mass of the sphere anyway. So that's what we are going to do anyway. It's a very short thing. We are not going to waste our time here. So that's what we have here. Horizontal component of tension. Since the angle theta of 27 is not between the tension and the side we are trying to resolve in the horizontal side, we use sine. And it is equal to mass times acceleration. So mass times acceleration, we know the mass, we know the mass. So to find the acceleration, we are going to divide both sides by mass. So the tension, as has been found, is 3.2 sine 27 divided by the mass of 0.29. This gives us 5 meters per second squared. So that is our centripetal acceleration. Now the next question says, calculate the period of the circular motion of the sphere. Now period can only be found by two equations, but when you're in this topic of circular motion, it can only be found by this equation. If you have to find period, you must know angular speed. Now what else are we given as data? We know centripetal acceleration. So, and we know that centripetal acceleration is a formula which has got angular speed. Angular speed, this seemingly W. So acceleration, centripetal acceleration is equal to R omega squared. Now omega, we know it. So omega squared will be squaring this part. That would give us omega squared. Omega squared would be squaring 2 pi over t, which becomes 4 pi squared over t squared, as I write here in place of omega squared. Then I make t squared subject to the formula. Then I square root both sides. I substitute where there is R, the radius, which you saw as 4.9 centimeters. So this becomes 0.049 meters. And also the centripetal acceleration of 5. We get the period of 0.62.